Welcome to continuous random variables, the concept that trips up almost everyone the first time. Today we're going to take what feels completely counterintuitive and make it crystal clear. We'll start from what you already know and build up step by step. Let's start with something familiar, rolling a die. A die has 6 outcomes, each with probability 1/6. This is a discrete random variable. The outcomes are countable, you can list them out, and every single outcome has a non-zero probability. Add them all up and you get exactly 1. Simple, clean, finite. But what happens when we can't count the outcomes? What about height? You could be 170 centimeters, or 170.5, or 170.53, or 170.537294. The values never stop. Height can take any value in an entire interval. It's uncountably infinite. If we try to assign non-zero probability to every single value, the total blows up past 1. So the probability of any exact single value has to be 0. We can't use the old framework anymore. We need a new one. Imagine a rope 1 meter long, representing all possible outcomes. You close your eyes and slice it at random. What is the chance you hit exactly the point at 0.5 meters? A single point has 0 length. Probability equals target length divided by total length, so 0 divided by 1 equals 0. Watch what happens as we shrink the interval from 1 centimeter to 1/10 to 100th. The probability shrinks right along with it. In the limit, the interval vanishes and so does the probability. Think of an uneven rod. Its mass density varies along its length, and the mass of any section is the integral of that density. Probability works the same way. The PDF f of x is not a probability, it is probability per unit length, just like mass density is mass per unit length. You never read a probability directly off the curve. Instead, probability equals density times interval width, which means you integrate. Memorize this. F of x is density, not probability. Start with a histogram of 1,000 heights. Using 10 centimeter bins, each bar's area equals the proportion in that bin. Now add more data and shrink the bins, 5 centimeters, then 2. The bars multiply and narrow, and their outline sharpens. As the sample grows without bound, and the bin width approaches 0, the jagged steps dissolve into a smooth curve, the probability density function. The area under this curve between any 2 points A and B gives the probability that x falls in that interval. That area is computed with an integral, the integral of f of x from A to B. Every valid probability density function must satisfy exactly 2 rules. First, the density f of x is always non-negative. You can never have a negative density, just like mass density is never negative. Second, the total area under the entire curve equals exactly 1. This is the normalization condition. The probability that x takes any value at all is 100%. These two properties define a PDF. The cumulative distribution function f of x tells you the probability that x is less than or equal to some value x. Geometrically, it is the area under the PDF from negative infinity up to x. Watch as we sweep x from left to right, the blue shaded area grows, and below the CDF curve climbs smoothly from 0 to 1, because it comes from an integral. The PDF is simply the derivative of the CDF. Notice how different this smooth curve looks compared to the staircase shape of a discrete CDF. Here is a property that surprises many students. For a continuous random variable, all 4 of these expressions are identical. P of A less than or equal to x less than or equal to b, with strict or non-strict inequalities in any combination. They all equal the integral of f of x from A to b. Why? Because p of x equals a is 0, so including or excluding a single point changes nothing. This is fundamentally different from the discrete case where each endpoint matters. Back to that rope, cut it at random, say at 0.3729. The probability of that exact point is 0. Yet it happened you did cut at a specific point. This is the crucial distinction. Probability 0 means almost never, not impossible. Probability 1 means almost certainly, not guaranteed. In the world of infinite possibilities, probability and possibility diverge. The simplest continuous distribution is the uniform Ondesoor. Its PDF is a flat horizontal line at y equals 1 constant density everywhere in the interval. Want the probability that x falls between 0.2 and 0.5? Just integrate the PDF, or equivalently, take the ratio of interval lengths. 0.5 minus 0.2 equals 0.3. The general formula is standard D minus C over B minus A. It's just a ratio of lengths. No sums, no point probabilities, pure geometry. The bell curve is the most common distribution in all of statistics. It has two parameters. The mean U controls the center, and the standard deviation sigma controls the width. Here is the rule of thumb. About 68% of data falls within 1 sigma, 95% within 2 sigma, and 99.7% within 3 sigma. The 68, 95, and 99.7 rule underpins everything from test scores to measurement errors across all of science. For continuous variables, the expected value uses an integral instead of a sum. You multiply x by f of x and integrate over the entire real line. Compare this to the discrete case. The summation sign just becomes an integral sign, and probability weights become density. Continuous is the infinitely refined version of the discrete world. Let's put discrete and continuous random variables side by side, and on the left, discrete bars at specific points, a staircase CDF that jumps at each value. Each point carries real probability mass. The sum of all bars equals 1. On the right, continuous, a smooth curve for the PDF, a smooth set CDF. No single point has probability. You must integrate the density over an interval. Countable versus uncountable. Sum versus integral. Steps versus smooth curves. Let's work a real example. Exam scores follow a normal distribution with mean 70 and standard deviation 10. First, notice the PDF peaks at f of 70 around 0.04, but remember, f of x is density, not probability. A single score has probability 0. Now, what fraction of students fail, scoring below 60? We standardize, z equals -1. The left tail gives about 16%. How many excel above 85? Z equals 1.5, so about 7%. And what about the middle range, 65 to 80? That captures roughly 53% of all students, the bulk of the class. Now the reverse question, what score do you need to be in the top 10%? We want k such that p of x less than or equal to k equals 8.9. From the standard normal table, phi of z equals 8.9. When z is approximately 1.28, undo the standardization. K minus 70 over 10 equals 1.28, so k is about 82.8. Score above 82.8 and you're in the top 10% of the class. This is how percentile thresholds work in practice. 3 things to carry with you. First, probability lives in intervals, not at individual points. It's about the length of the region, not the count of dots. Second, density is not probability. You get probability by integrating density over a range. Third, probability 0 does not mean impossible, it just means almost never in the infinite continuous world. Continuous random variables. Now you know.